On August 6, 2025, the James Webb Space Telescope slammed into emergency mode to capture an object that, honestly, just shouldn't exist. Astronomers, including the Pan-STARRS team over in Hawaii, expected a dying ball of ice. Instead, Webb's new data on the interstellar Comet 3I Atlas just confirmed a chemical nightmare. This visitor isn't just unusual, it's breaking every rule in the book, and the deeper the data goes, the more unthinkable the questions get. Let's explore this together. Emergency override, Webb's unprecedented response. What does it take to stop the world's most powerful space telescope dead in its tracks? On August 6, 2025, we found out. When the alert came from the Pan-STARRS survey, led by principal investigator Ken Chambers, the numbers were, well, alarming. The interstellar object 3I Atlas was accelerating, its spectrum flashing with unexpected metals. There was no time for committees. In a move almost unheard of, a director's discretionary time override was triggered, sidelining Webb's entire multi-million-dollar schedule. This wasn't a normal target of opportunity, this was an emergency. The command chain went straight to the Space Telescope Science Institute director's desk, requiring unanimous approval. It was a massive risk. A single unscheduled slew of that magnitude can cost over 12 hours of precious observation time and risks thermal shock to the delicate mirror segments. This time is meticulously allocated to dozens of other research teams who have waited years for their shot. At 2:17 GMT, after a rapid 38-minute repointing maneuver, the command went live, the tension palpable in the Baltimore control room. Webb's instruments locked onto an object that was already beginning to rewrite cosmic chemistry. Fewer than 4 such overrides have happened in Webb's entire operational history. None for an interstellar object. Early activity beyond Jupiter's orbit. Here's the first red flag that 3I Atlas was no ordinary comet. It woke up in the deep freeze. Most comets are quiet until they cross inside the solar system's frost line near Jupiter's orbit, roughly 5 astronomical units from the sun. But 3I Atlas was already active at 6.8 AU, far out where the sun is just too weak to sublimate water ice. Ground-based telescopes, following up on alerts from observers like Karen Meech at the University of Hawaii, noted a persistent brightening of 0.3 magnitudes in just 48 hours. For an object this distant, that represents a massive increase in its gas and dust output. This sustained activity, producing a tenuous coma when the surface temperature was below 150 degrees Celsius, pointed to a body born in a place fundamentally different from our own solar system. Its engine had to be a hyper-volatile ice, something that turns to gas in the slightest warmth of the distant sun. The comet's tail grew at a pace that honestly stunned the teams watching, driven by gases that simply shouldn't have been active so far out. It was the first clue that the chemistry of this visitor, as cometary expert Michael Mumma might put it, was deeply, profoundly wrong. The carbon dioxide anomaly. When Webb's near-infrared spectrograph delivered its first data packet, the anomaly was impossible to miss. The absorption band at 4.26 microns was breathtakingly strong. It's the classic textbook signature for carbon dioxide, and it utterly dominated the spectrum. The final analysis confirmed a carbon dioxide to water ratio of 8:1. That isn't just an anomaly, it's a statistical impossibility based on every comet we have ever studied. For context, even the most carbon dioxide-rich comets in our system barely reach a ratio of 0.3. The gas production rate was staggering, calculated at over 1.5 times 10 to the 28th molecules per second, an output comparable to what the great comet Hale-Bopp produced when it was much closer to the sun. Every cross-check from Hubble and the Keck Observatory confirmed it. This isn't a calibration error, it's a message, as a planetary scientist like Stephanie Milam at NASA would argue, from a star system where the chemistry of planet formation was completely inverted. Such a system might have formed around a carbon star, creating a world where carbon dioxide, not water, is the dominant ice. Nickel without iron, an impossible chemistry. This is where the story goes from strange to deeply unsettling. As the team at the European Southern Observatory analyzed the high-resolution spectra, they found clear emission lines for atomic nickel at 3,415, 3,524, and 3,525 angstroms. The real shock was what was missing. Iron. In every celestial body ever studied, nickel and iron are chemically inseparable, forged together in the hearts of dying stars and scattered in a cosmic ratio of about 1 part nickel to 15 parts iron. Yet even with the Very Large Telescope's UVES instrument running at a resolving power of 80,000, iron was a ghost. The data was brutal. The upper limit on iron atoms meant nickel outnumbered it by more than 40 to 1. Spectroscopists like Neil Dello Russo at Johns Hopkins would confirm this is unprecedented. The only plausible, though exotic path is the molecule nickel carbonyl, which is so volatile it vaporizes at just 43 degrees Celsius. This molecule is extremely fragile and would break down under solar radiation, releasing the free nickel. But for that to be the explanation, the object had to form in a place that chemically isolates nickel on an industrial scale, a process unknown in nature. Trajectory anomalies and acceleration spikes. As if the chemical puzzle wasn't enough, the way 3I Atlas moved was just as bizarre. Davide Farnochia's team at JPL, who are masters of celestial mechanics, flagged its trajectory before the Webb data even came down. The object wasn't just following the clean arc of gravity. It was accelerating. Over a 72-hour period, its velocity increased by nearly 0.12 meters per second squared, a non-gravitational push far beyond what the observed outgassing could explain. The thrust calculated from the gas production rate was an order of magnitude too low to account for the observed change in speed. The data also showed tiny sharp jumps of up to 1.5 meters per second, as if an internal force was flickering on and off, rather than a steady, continuous jet. This stands in stark contrast to Oumuamua's smooth acceleration. For an 11-kilometer-wide body with an estimated mass of over 1 trillion kilograms, this erratic push is like watching a mountain suddenly lurch forward with no visible cause. The physics just doesn't add up. The acceleration was real, and it wasn't coming from ice alone. The lighthouse effect. Mechanical light curves. Every object in space tumbles, but 3I Atlas's light curve is anything but natural. Photometric data from NASA's TESS satellite revealed a periodic brightening that pulsed with the precision of a clock, sweeping like a lighthouse beam every 7.2 hours. A tumbling potato-shaped rock would produce a smooth rolling sine wave of light. This was a square wave, ramping up in brightness by a full 1.8 magnitudes in just under an hour, holding steady, and then dropping off sharply. This implies an object with distinct flat sides and sharp edges, unlike the irregular shapes of natural bodies. Furthermore, outgassing should create torque, causing the object's spin period to change over time. Instead, the 7.2-hour period remained locked in to within 1,000th of a second, a major physical contradiction. An expert on exoplanet light curves like MIT's Sarah Seeger would immediately recognize this as unnatural. The sharp increase in brightness also hints at a highly reflective, possibly metallic surface being periodically revealed to our line of sight. Ancient sky metal. Historical context. You know, the idea of strange metal falling from the sky is actually woven into our oldest histories. Around 3200 BCE, ancient Egyptians hammered beads from iron they couldn't have possibly smelted. These beads, discovered at Gertze, are nearly 30% nickel. It's a kind of cosmic fingerprint proving they were made from a meteorite. Centuries later, a dagger was buried with Tutankhamun around 1323 BCE, and its untarnished blade contains 11% nickel. The Egyptians called this material Baya on Pet, or iron from heaven, with a hieroglyph that actually combines sky and metal. Further afield, the Inuit of Greenland used the Cape York meteorite for centuries as a source of iron for tools and harpoons. And as historian Lydia Baum of Heidelberg University notes, these cultures knew this metal was not of the earth. It was seen as a gift, or maybe even a warning, from the gods. This ancient reverence for rare, otherworldly materials really mirrors the intense scientific focus on the anomalous metals being broadcast by 3I Atlas today. A.V. Loeb's challenge to consensus. You can't have a conversation about interstellar anomalies without Harvard astrophysicist Avi Loeb. When the data on 3I Atlas came out, he immediately argued in a new preprint that these are all potential hallmarks of something engineered. In the lab, separating nickel from iron is done via the Mon process, which, kind of eerily, uses carbon monoxide to create volatile nickel carbonyl, the exact chemistry hinted at in the comet's coma. Loeb argues that while the community scrambles to invent exotic natural comets, We must apply Occam's razor. Is it simpler to invent new astrophysics, or to consider an existing category of object we've theorized about, technology? His critics rightly say extraordinary claims require extraordinary evidence. But Loeb's position, now supported by his Galileo Project initiative, is that the evidence is already extraordinary. The project's mission is to actively search for technological signatures, and 3I Atlas fits the profile of exactly what they are looking for. Clinging to familiar explanations when the data screams otherwise is a failure of scientific imagination. Scientific community divided. The revelations about 3I Atlas have sent shockwaves through the astronomical community. On one side, scientists like Michelle Bannister of the University of Canterbury are pushing for natural explanations. They propose that 3I Atlas could have formed in a carbon-rich protoplanetary disk around a carbon star, where unique chemical conditions, while improbable, might allow for the formation of nickel carbonyls. It's a theory that pushes the boundaries of known astrophysics but keeps the object within the realm of the natural. On the other side, a growing number of researchers, emboldened by the sheer number of anomalies, are starting to take the artificial origin hypothesis seriously. They argue the combination of its 40-to-1 nickel-to-iron ratio and mechanical light curve is too much to be a coincidence. The debate is raging on preprint servers like ArcSiv, with some suggesting it could be a probe, a solar sail fragment, or even derelict industrial material from another civilization. This isn't an angry argument, but a rigorous process where every theory is being stress-tested against the hard data. NASA's High Anomaly Classification. Officially, NASA's Planetary Defense Coordination Office under Lindley Johnson has flagged 3I Atlas as a high-priority scientific object. While it poses no impact threat, its trajectory is being monitored by JPL's Sentry 2 system with an unusual condition code 9, indicating a trajectory so unpredictable it defies reliable long-term projection. This flag essentially tells the entire astronomical community that all bets are off for where this object will be in the future, making follow-up observations extremely difficult and urgent. Internally, this triggers discussions at the highest levels of NASA's Planetary Science Division about the fundamental nature of the object. It becomes a question not just of tracking, but of understanding. The tension between the cautious public statements and the urgent internal scramble to understand what they are dealing with is palpable. The official line is more data needed, but the unofficial reality is that this object is an enigma of the highest order. So what is 3I Atlas? Is it a cosmic fluke, a messenger from a type of star system we've never imagined, with a chemistry that rewrites the rulebook? Or is it something more? Is this the first truly unambiguous sign that we are not alone in the universe? A piece of technology coasting through our solar system? The data is tantalizing, troubling, and refuses to give us an easy answer. For now, the truth hangs in the balance, waiting for the next round of observations to tip the scales one way or the other. What we do know is that this visitor from the dark has changed the conversation forever. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. What do you think 3I Atlas is? Let us know in the comments below. Thank you for watching Simply Science. What if the third interstellar visitor ever discovered was not a comet, but a billion-year-old alien messenger? In the summer of 2025, a faint object designated 3I Atlas streaked into our solar system, and a controversial hypothesis immediately captured the world's attention. This was no ordinary rock. The idea of advanced alien technology made global headlines, but NASA quickly stepped in with a powerful, evidence-based response that settled the debate. So what did they find? Let's explore this together. The Atlas discovery in Chile. So, how do we even spot these interstellar travelers in the first place? It starts with a constant, vigilant watch of the night sky. The story of 3I Atlas began on July 1, 2025, at an observatory in Chile. There, a robotic survey system named ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, detected a faint object at an apparent magnitude of 20, making it about 2.5 million times fainter than the faintest star visible to the naked eye. Led by principal investigator John Tonry, the ATLAS system is a NASA-funded project developed by the University of Hawaii, using its twin half-meter telescopes to scan the entire visible sky every 24 hours. When astronomers calculated the object's trajectory, they saw it was following a sharply hyperbolic path with an orbital eccentricity greater than 1. a definitive sign it wasn't gravitationally bound to our sun. Its orbit was an open curve, meaning it came from deep space and was destined to return there. The object was named 3Y Atlas, with the 3I marking it as the third interstellar object ever discovered. It was racing through our system at a stunning hyperbolic excess velocity of 35 kilometers per second, a truly exceptional catch and a prime target for immediate scientific study. A.V. Loeb's controversial hypothesis. Here's where the story takes a sharp turn into speculative territory, thanks to a bold proposal from Harvard astronomer Avi Loeb. While most scientists saw a fascinating natural object, Loeb, known for his controversial work on Oumuamua, offered a different interpretation. In a scientific paper posted to the ArXiv preprint server, Loeb pointed to the object's early lack of a visible coma and its trajectory. He suggested that if the comet continued to show no outgassing, or if its path deviated from a purely gravitational path without a visible tail to explain the push, it could be evidence of something artificial. He even raised the hypothetical possibility of malign intent, though he stressed this was an intellectual exercise meant to keep science open to radical possibilities. His argument, similar to the one he made for Oumuamua, hinged on the idea that any non-gravitational acceleration without a visible coma required a novel explanation. He proposed that a solar sail, a thin, lightweight craft pushed by the pressure of sunlight itself, was one such possibility that science should not be afraid to consider, however unlikely it might seem at first. The physics of radiation pressure are well understood, but for it to be effective, an object must have a huge surface area and an extremely low mass, characteristics not found in natural bodies. Media sensation versus scientific method. Here's the thing about alien theories: they travel faster than light speed in the media. Avi Loeb's hypothesis for 3I Atlas was sensational. Headlines around the world, from online blogs to major news networks, quickly latched onto the most dramatic elements of his proposal: the possibility of an alien craft with potentially hostile intentions. This created a fascinating public spectacle but also highlighted a fundamental tension in how science works. The scientific method is a slow, methodical process that can take months or even years of observation and peer review before any conclusion is reached. In stark contrast, the news cycle operates in mere hours. The global conversation was suddenly centered on a dramatic, unproven idea, while the painstaking work of collecting hard data was just beginning. This put NASA in the position of having to respond not just to a scientific hypothesis, but to a worldwide media event fueled by one of the most compelling questions in human history. It was a classic case of exciting speculation, published on a preprint server before peer review, getting a massive head start on the deliberate evidence-based investigation. This gap between speculation and verification is where misinformation can thrive. NASA's comprehensive investigation. With the debate raging, NASA and its international partners marshaled their most powerful instruments. This wasn't a casual glance, it was a coordinated multi-platform investigation led by Tom Statler, NASA's lead scientist for small bodies. The agency dedicated priority time on the James Webb Space Telescope, using its near-infrared spectrograph or NIRSpec to perform detailed chemical analysis of the gases in its coma. Simultaneously, the Hubble Space Telescope's Wide Field Camera 3 was used for high-resolution imaging to search for any faint dust or fragmentation events with its superior resolving power in visible and ultraviolet light. On the ground, a network of observatories, including the twin 10-meter mirrors of the Keck Observatory in Hawaii, began a long-term monitoring campaign to track its brightness and trajectory with pinpoint accuracy. The goal was to leave no stone unturned, to precisely measure its path to within a few milliseconds, to analyze its chemical composition, and to study its light curve for clues about its shape and rotation. This multi-wavelength, multi-observatory approach is the gold standard in modern astronomy for characterizing a novel object. Comet behavior confirmed. So what does a comet actually do when it gets close to the Sun? The answer to that question was the key to solving the 3I Atlas mystery. As the object continued its journey inward, NASA's array of telescopes watched its every move. The findings were unambiguous. By late July 2025, as it crossed inside the orbit of Mars, 3I Atlas started to behave exactly like a comet. It developed a glowing coma, a fuzzy atmosphere of gas and dust, that eventually grew to over 100,000 kilometers in diameter. Soon after, it began to sprout a tail of dust and gas stretching for millions of kilometers, pushed away from the nucleus by the solar wind. Dr. Lori Glaze, director of NASA's Planetary Science Division, summarized the findings clearly, stating that the object was exhibiting all the classic signs of a comet, reacting to the sun's energy. Its initial lack of a tail was simply because it was too far from the sun for its ices to sublimate. The final verdict from the data was it looks like a comet, and it acts like a comet, so there was no need for an exotic, artificial explanation when a natural one fit the observations perfectly. Chemical composition analysis. But confirming it was a comet was just the beginning. The real prize was in its chemistry. A team led by Dr. Anjali Sharma, a planetary scientist at NASA's Goddard Space Flight Center, used the James Webb Space Telescope spectrographs to break down the faint light from the coma into its chemical fingerprints. The analysis revealed familiar substances like water ice and carbon dioxide, but with a major surprise, 3I Atlas had an unusually high ratio of carbon dioxide to water, measured at nearly 35%. This vital clue suggested the comet must have formed in an extremely cold region of its home star system, far out in its protoplanetary disk where carbon dioxide could freeze out in large quantities. Furthermore, analysis of the dust grains showed a polarization signature with negative branching at a phase angle of 22 degrees, suggesting a surface composed of very fine, porous, fluffy dust grains, a sign of a very pristine, unaltered body. This fluffiness implies the grains have not been heavily processed by heat or collisions, making them a near-perfect sample of their native environment. This chemical snapshot provides invaluable data for models of planetary formation in other star systems. Trajectory and safety assessment. With all the talk of alien technology and, possible malign intent, a critical question had to be answered. Was this object a threat to Earth? The bottom line is a definitive no. NASA's Jet Propulsion Laboratory, or JPL, used the global observation data to refine the comet's trajectory with pinpoint accuracy. Their calculations, made public through the Center for Near-Earth Object Studies, showed its closest approach to Earth would be a distant 1.8 astronomical units, which is roughly 170 million miles. There was never any risk of impact. The comet's orbit was also highly inclined at 60 degrees relative to the ecliptic plane, the flat disk where the planets orbit, meaning it was passing high above the main traffic of the solar system. Its perihelion, or closest approach to the Sun, was calculated to be a safe 1.5 AU, well outside of Earth's orbit. NASA's Planetary Defense Coordination Office was therefore able to declare with certainty that this object posed zero threat. This precise tracking dismantled any notion that the comet could be a danger, allowing everyone to focus on the science. Natural anomalies in cometary physics. So the whole 3I Atlas controversy really boils down to a single fundamental question in science. Is an anomaly evidence of something artificial, or is it a sign of a natural process we haven't encountered before? Science almost always bets on the latter. Our own solar system is filled with comets that behave in bizarre ways. Take Comet 29P Schwassmann-Wachmann, which can increase in brightness by over 15 magnitudes, a factor of 1,000,000, in just a few hours due to cryovolcanic eruptions. Another example was Comet C 2019 Y4, or Atlas, a different comet which unexpectedly disintegrated into multiple pieces as it approached the Sun, showing how fragile these icy bodies can be. The point NASA scientists made is that unusual traits are not automatic evidence of engineering. They're part of the normal, messy, and fascinating physics of icy bodies. These anomalies are not problems for science, they're actually the very data points that lead to new discoveries about how objects form and evolve. So the unique chemistry of 3I Atlas isn't a paradox, it's a clue. Scientific value of interstellar visitors. So, if 3I Atlas is not alien technology, why is it so important? Well, it's because interstellar comets are windows into other worlds. Each one is a preserved time capsule carrying the precise chemical and physical fingerprints of the environment where it formed. For 3I Atlas, the dominance of carbon dioxide and its trajectory suggest it could be over 7 billion years old, originating from the Milky Way's thick disk, a population of ancient stars that existed long before our sun was born. By studying its isotopic ratios, like the deuterium to hydrogen ratio in its water, scientists can get direct clues about the water in other primordial solar systems, which is a key factor in assessing the potential for life elsewhere. This is more than just a curiosity, it's a preserved fragment of another planetary nursery. Future missions like the ESA's Comet Interceptor are being designed specifically to launch and wait in space, ready to chase down the next interstellar visitor for an even closer look. These objects represent a fundamental shift from studying other solar systems through the faint light of their stars to actually analyzing physical samples. Comparing three interstellar objects. Let me explain why having more than one of these visitors is so crucial. By comparing them, we can start to build a bigger picture of the galaxy. 3. I-Atlas was the third interstellar object detected, and it's fascinating how different all three have been. The first one, Oumuamua, was highly anomalous rocky, appearing to have an extreme 10:1 aspect ratio, and showing no visible coma, which is what led Loeb to his original theory. The second, 2I Borisov, discovered by amateur astronomer Gennady Borisov, was almost the opposite. It looked and behaved very much like a standard long-period comet from our own Oort cloud, with a chemical composition, specifically a carbon monoxide to water ratio of about 0.3, that was remarkably familiar. 3I Atlas falls somewhere in the middle. It clearly behaves like a comet, but its distinct chemical ratios and light-scattering properties make it stand out as unique. This diversity is exactly what astronomers hope to find. It allows them to test whether the processes that shaped our home system are typical, or if we are an outlier. In the end, Comet 3. I-Atlas wasn't an alien messenger, but it did bring an incredible message. It wasn't science fiction, but it delivered profound science. It carried the chemical secrets of its birthplace, a star system far from our own, giving us a rare glimpse into the diversity of worlds forming across our galaxy. The real story isn't about a manufactured object, but about the natural wonder of the universe and our growing ability to study it. If you want more deep dives into the biggest discoveries from space, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting for us. Thanks for watching Simply Science. Something just outran the stars over Mars. In October 2025, a camera on the Perseverance rover captured a flash moving at a blistering 60 kilometers per second. This was no meteor. It perfectly matched the speed and timing of interstellar visitor 3I Atlas during its historic flyby. Then, the Mars orbiters tasked with watching it went dark. The raw images vanished. Unconfirmed reports of multiple objects and a strange, inexplicable green glow set the scientific world on edge. The 60-kilometer streak. How do you spot a ghost in the machine? In early October 2025, the global astronomy community was electrified by a time-lapse posted from Perseverance's public image archive. It showed a single razor-thin streak cutting across the Martian starscape. The calculated velocity was an astonishing 60 kilometers per second, or over 1,034 miles per hour. That's more than double the speed of Mars itself in its orbit around the Sun. To put that in perspective, NASA's Parker Solar Probe, the fastest object humans have ever built, only hits its top speed deep in the Sun's gravity well. This object was maintaining that velocity out at Mars. The astrometric analysis was sound. The streak's motion was measured frame by frame against background stars, ruling out a simple camera artifact or cosmic ray. This process echoed the legacy of observers like Gennady Borisov, the amateur who discovered the second interstellar comet, 2I Borisov, in 2019 from his own backyard observatory, proving that monumental discoveries can come from anywhere. The calculation was undeniable. If the 60 kilometers per second speed was correct, the track matched the predicted path of 3I Atlas almost perfectly. The discovery was out, but the burden of proof had just begun. Crowdsourced chaos. What happens when a mystery goes viral? As soon as the Perseverance time-lapse hit the internet, forums and social media exploded. Hundreds of independent analysts downloaded the raw frames, running their own scripts to either confirm the streak or debunk it. The debate instantly fractured. Some groups not only reproduced the main track, but also claimed to find hints of secondary, faster-moving objects in the data from the following day. Others, using different noise reduction pipelines, saw nothing but static. Then, at 3 minutes past midnight UTC, one team's stacked animation showed a brief, anomalous green flash, centered at a wavelength near 510 nanometers. Speculation ignited. Was this a genuine emission from the object, or just a cosmic ray strike amplified by aggressive image processing? Rival teams argued over color calibration and the signal-to-noise ratio, which was barely above the detection threshold. This is the modern face of discovery, championed by figures like Dr. Chris Lintott of the Zooniverse Project, where millions of citizen scientists help process raw data from telescopes. But without a clear institutional signal to validate the findings, this crowdsourced effort was descending into pure chaos. Mars's front row seat. Why was Mars the perfect place to watch this interstellar show? For a brief window in early October, Mars and its fleet of orbiters had the best view in the solar system. 3 key spacecraft were tasked with observing 3I Atlas as it passed 9 million kilometers away. NASA's Mars Reconnaissance Orbiter with its powerful high-rise camera, the European Space Agency's Trace Gas Orbiter, and the veteran Mars Express. Let me explain the challenge here. At that vast distance, even high-rise, a camera with a resolution of 30 centimeters per pixel on the Martian surface would see the object as a smudge just a few pixels wide, with a best-case resolution of nearly 50 kilometers per pixel. The team, led by planetary scientist Dr. Alfred McEwen, had to reprogram the orbiter, which completes a full orbit every 112 minutes, to aim at a tiny, fast-moving target against the blackness of deep space. This required slewing the entire spacecraft off its normal downward-looking orientation, a complex and risky maneuver. Each snapshot was a calculated gamble, with exposure times carefully balanced to avoid saturation or motion blur. Aim too early, and you get empty space. Aim too late, and the object has already vanished from the frame. It was a race against geometry and time, and these orbiters were our only eyes. The silent archives. So, where did the data go? In the days following the flyby, an unnerving silence fell over the public data archives. Normally you'd expect images from major events like this, especially from Mars orbiters, to pop up within a few days in their raw, uncalibrated form. But this time, there was nothing. No files from HiRISE. No quick-look frames from Mars Express. The silence from official channels was absolute. Inside the Jet Propulsion Laboratory, the imaging teams were facing immense pressure. You see, the delay wasn't just bureaucracy. Processing data from a faint object moving at 60 kilometers per second is a nightmare. Standard software pipelines, designed for static Martian landscapes, break down completely. As Dr. Rita Beebe, a pioneer of NASA's planetary data system, could attest, cleaning and validating this kind of data for public release is a painstaking process that can take weeks. Releasing images with uncorrected geometric distortion or without proper flat fielding could create artifacts that look like real objects. The data downlink rate from Mars, often limited to less than 2 megabits per second, created a huge bottleneck for the gigabytes of raw data. Wait too long, and you fuel accusations of a cover-up. Every pixel had to be perfect. Green without dicarbon. Can you have fire without smoke? In cometary science, a green glow is usually an open and shut case. It's the signature of dicarbon, or C2, a simple molecule that glows bright green when sunlight breaks it apart, creating telltale spectral features called swan bands, especially the bright one at 516.5 nanometers. It's so reliable that astronomers call it a comet's chemical calling card. But this is where the story of 3I Atlas gets strange. The unconfirmed green flash reported in the Perseverance frames implied dicarbon was present, but the first trickle of provisional spectral data from the Mars orbiters hinted at the exact opposite. The emission bands at both 516.5 and 563.5 nanometers, where dicarbon should have been, were weak, or missing entirely from the spectrum. In a laboratory, a green glow without dicarbon is a flat-out contradiction. Veteran comet expert Dr. Michael Oumuamua of NASA has spent his career analyzing these chemical fingerprints, and standard physics has no easy explanation for this. It would require a completely new chemical pathway, perhaps involving other ionized elements to produce that color. The question became a battleground. Was the green flash a real, physics-defying event, or just a ghost in the data? Without the final, calibrated spectra, the paradox remained unsolved. Chemistry that defies models. What if this visitor isn't playing by our rules? The spectral data that eventually emerged from the Mars campaign was a direct challenge to textbook comet science. First, reports from the Mars Express team highlighted a chemical fingerprint dominated by nickel, not iron, at a ratio never before seen. In all known solar system comets, which are largely composed of water ice and iron-rich silicates, iron is far more abundant. Here, the nickel signature towered over everything else. Then, the trace gas orbiter found that the object was spewing out vast amounts of carbon dioxide, with a CO2 to water vapor ratio exceeding 10:1. For a comet, water should be the dominant gas. This chemistry was already strange, but the images revealed something even weirder. The object had a plume, a jet of material, blasting forward toward the sun. This defies normal cometary behavior. This anti-sunward jet was sharp and well-defined, not the broad, fan-shaped tail we expect. As Dr. Karen Meach, who led the study of our first interstellar visitor Oumuamua, knows well, these objects can shatter our expectations. The data implied 3I Atlas was incredibly dense, with a calculated mass of at least 10 billion tons, more like an asteroid than a fluffy comet. Each new piece of data made natural explanations harder and harder to justify. The WOW signal coincident. Could a 72-second radio anomaly from 1977 be linked to this? Harvard astrophysicist Dr. Avi Loeb, known for pushing the boundaries of interstellar research, entered the debate with a provocative calculation. His team traced the path of 3I Atlas backward in time, and found that its trajectory through space overlapped with the location of the famous 1977 WOW signal, detected by the Big Ear Radio Telescope in Ohio. The WOW signal was a powerful, 72-second radio burst at 1420.4 MHz, the precise frequency of neutral hydrogen. It's long been considered the most promising candidate for an artificial, extraterrestrial signal, precisely because nature doesn't typically broadcast on such a narrow, specific channel. The researcher who discovered it, Jerry Amon, was so impressed he circled the data and wrote, "Wow," next to it. Loeb's team calculated the odds of a random interstellar object passing through those exact coordinates as just 0.6%. That's rare, but not impossible. Skeptics in the SETI community urged caution, pointing out the risks of finding patterns after the fact. Still, the tantalizing connection, championed by a figure behind initiatives like the Galileo Project, made the object a prime target for radio follow-up. 5 weeks in solar shadow. Just as the mystery peaked, the object vanished. After October 29th, 3I Atlas slipped behind the sun, entering a communication blackout zone. This is a normal part of orbital mechanics called solar conjunction, where the sun's glare makes observation from both Earth and Mars impossible. For 5 long weeks, every telescope was blind. Scientists, amateurs, and SETI researchers could only watch the calendar and wait for early December 2025, when the object was predicted to re-emerge into the pre-dawn sky. Experts in orbital mechanics like JPL's Dr. Davide Farnocchia, whose ephemeris data is the lifeline for these campaigns, had provided the precise calculations, but everything depended on what the object did while it was out of sight. 4 key questions hung in the air. Would its brightness have changed, indicating fragmentation? Would its trajectory have shifted, hinting at outgassing or even maneuvering? Would its strange sunward jet still be there? This brief observational window in December would be decisive. Everyone was waiting to see what would emerge from that solar shadow. The evidence ladder. How do we separate a real signal from wishful thinking? In a situation this chaotic, scientists rely on a ladder of evidence. At the very bottom rung is repeatability. A genuine streak or flash must appear in independent analyses from different teams using different software, all matching the same time and location. The next rung up is multi-band confirmation. A real physical object should show up in different color filters and wavelengths, from infrared to ultraviolet, not just flicker in a single visible light channel. Above that, you have geometric and dynamic proof. If there are multiple objects, they must move in parallel, following predictable orbits. The highest and most difficult rung is evidence of artificiality, what is sometimes called the Sagan standard. As the great science communicator Dr. Carl Sagan famously said, "Extraordinary claims require extraordinary evidence." This means looking for something that requires a 5 sigma level of statistical confidence, the gold standard for a discovery in particle physics. This would be something nature simply cannot do: deliberate maneuvers, repeating geometric patterns, or a narrowband radio signal. Every anomaly associated with 3I Atlas had to climb this ladder, and the burden of proof grew heavier with every step. An unresolved puzzle. So, where does this leave us? The facts on the table are a stack of powerful anomalies. 3. I-Atlas showed a chemical makeup that challenges our models of comets, with its strange nickel-to-iron ratio and a 10-to-1 dominance of carbon dioxide over water. It displayed a massive anti-sunward plume that defies our understanding of cometary dynamics, and its trajectory carries a statistically rare, though unproven link to the 1977 WOW signal. Yet the most critical evidence, the high-resolution images and complete spectral data from the Mars flyby, remains closely held by the world's space agencies as it undergoes rigorous calibration. As the object heads toward its perihelion, its closest approach to the Sun, the forces acting upon it will be at their peak. Dr. Jill Tarter, a pioneer at the SETI Institute, has spent a career reminding us that this work requires patience and rigorous skepticism. For now 3I, Atlas remains an interstellar puzzle. We have a compelling collection of clues, but no confirmed answers. The only thing certain is that the mystery demands we keep watching. The universe rarely gives up its secrets easily. The story of 3I Atlas is a perfect example of how one object can challenge everything we think we know about our place in the cosmos. Is it a new class of comet, a natural phenomenon we've never seen before, or something else entirely? Only more data and more scrutiny will tell. What are your thoughts on this interstellar mystery? Let us know in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the biggest questions in space. Thanks for watching Simply Science.